chirality to fabricate 3 or less generation of 3-dimensional display devices. In the field of catalysis, actually, we are focused trying to integrate 2 types of different nanoparticle building blocks in the same assembly structures, and we try to use the interactions between these 2 types of different nanoparticles and trying to tune the interactions. For example, the electric transfer interactions, and then we want to realize we improve the selectivity as well as activity in the catalyzing the electrochemical, thermochemical, and photochemical reactions. Today, I would like to talk about how we can use the self-assembly strategy in the memory separation. If you talk memory, every people here know at least we can divide it into several types, like microfiltration, ultrafiltration, nanofiltration, and reverse osmosis, with the order of increasing the selectivity. For instance, the reverse osmosis has the highest selectivity, being able to separate the monovalent ions from the aqueous solution. However, if you check all the reported memory separation methods, you found that the lack of the ability to separate the molecules and the ions with identical size and charges. So we suppose the next big challenge in the future is how we can realize the high precision separation of small molecules and the ions. So in order to separate the molecules and the ions, we think we need to develop some new transport mechanism in nano-confinement space. So if you check, these are totally different with conventional continuous transport theory in large space. I mean, the process size is larger than 10 nanometers. Actually, we found in this nano-confinement space, the continuous equation doesn't work anymore, and new properties emerging. So our works about the separation memory with ion or molecular precisions are divided into 2 parts. In the first part, we focus on so-called nanofluidic systems. We want to explore the new transport mechanism in the nanofluid systems, and want to increase the permeance as well as the selectivities. The second part, we based on memory application, especially in separating the small organic molecules. So the first part, today I will introduce nanofluidics in porous monolayer membranes. So in 2020, Nature Material published a comment on the advent of nanofluidics. They point out to biomimic the biological machinery, one would need to go beyond the ionic response of individual channels and fabricate the devices that can incorporate many of these channels. Unfortunately, if you check the neat pages, you will find that most work have been done on the individual or single channels. For instance, the pores around the 1-dimensional nanotube or the 2-dimensional graphene slits. There indeed have some reports about the multiple systems based on feeding the hull on the graphene. Whatever all the reported results are lack of the high porosity, the uniform pore size. So we propose a new strategy as we call interfacial pre-assembly and the polarization method. We want to fabricate the monolayer memory also with orderly arranged pore and uniform pore size. So we found this types of porous monolayer membrane are of some unique properties such as low resistance, strong coupling effect, the bigger Coulomb blockade, and the higher ion molecular selectivity, as well as the faster water acceleration. The first example, we demonstrate the strong photocoupling effect caused by small interpore distance. If you check literature, you found a very important, there is like a debate on so-called salinity polarization. So if you extrapolation from the single pore system to multiple systems, you found will be fair because the reason is quite simple. When you increase the pore density from the single pore system to multiple systems, you will find a stronger so-called concentration polarization effect. That means across the membrane, actually you are harder to maintain the concentration gradient. As a result, such a strong concentration polarization effect has been believed as an insurmountable bottleneck for the salinity power generation. However, if you check the Nernst-Planck equation carefully, except for this first item related to concentration polarization, you will find the second item, this one related to surface charge. So from the second item, you will say if you can increase the pore coupling, actually you can increase the self-dependent potential, then you might suppress the concentration polarization effect. So we further do some detailed theoretical calculation. We studied the relationship between the spacing of two charged surfaces and the distance of electrostatic interaction. We also conquest divergence. As we choose the right side, we found when the spacing of two charged surfaces is less than twice of the divergence, we will find the rightmost part, actually the surface potential will be increased. That means we may separate the strong concentration polarization effect. So to testify this hypothesis, we fabricated the porous so-called covalent organic framework called monolayer membranes. We found that these covalent membranes are of the highest pore density, reaching 13 power 10 square centimeters. And this higher pore density actually comes from the short interpore distance. We further do some theoretical calculation. We found that at the very small interpore distance, like less than 5 nanometer, you will find a strong pore coupling. As a result, the membrane conductance will increase and they can get the suppressed current decay. That means we have got the hope to overcome the bottleneck. As a result, we actually obtain the record high output power density of 136 watt per square meter, which is much larger than the previously reported result. We can further increase the output power density by change or by tuning the surface charge through the change the middle metal side. We can say finally within the proper TBP Prof monolayer membrane, we obtained the output power density of near 350 watts per square meters. So we also found in this multiple system, or also called as the high permeability system, we found an anomalous coupling effect between the fluid field and the electric field. We found in these high permeability systems, actually, because of the fast depletion of the capacitive layers, so the ions in the electric double layers will be moved or cross the membrane. This will causing the generation of the reverse stream current. As a result, the membrane conductance will decrease. So this phenomenon is totally opposite to that we observed in single pore systems. I think there's a large difference between the multiple system and the single pore systems. So in this multiple system or high permeability system, in the absence of the electric field, the stream current originates from the membrane selectivity. So as the left picture shows, actually we found the direction of the stream current strongly dependent on the gas direction. Here is the gas pressure flow. So we can see along the positive gas pressure flow, you can see the increase the stream current, otherwise the stream current will decrease. However, under the electric and the fluidic coupling system, the stream current no longer depends on the pressure direction. Actually, they are always opposite to the electric field direction. As shown in the middle picture, you will find always the decreased stream current, whatever the direction of your gas pressures. So what's the reason? So we use the continuous remote simulation. We found the fast dissipation of the capacitive layers will drive the ions to move or cross the membrane, thus to decrease the membrane conductance and also reduce the streaming current. Our simulation result on both electric current and the streaming current match well with our experiment result. Next, we construct Angstrom scale dynamic hydrogen pore by trapping the hydrogen ions like potassium, sodium, and lithium into the inside of the pores. So we found a new transport mechanism totally different with the biological channels. So in the biological channels, all the people knows the dehydration process always governs the monovalent ion selectivity. However, in our hydrogen pores, we found we achieved the fast and selectivity of the monovalent ions in their hydrogen rather than dehydrated state. So firstly, we found that significant difference in the permeability of three types of the monovalent ions, including the potassium, sodium, and lithium. We also can follow the orders of the potassium is larger than the sodium, larger than the lithium. To be specific to the potassium, actually, we found a very low transmembrane barrier. So we obtained the higher lithium, potassium and lithium selectivity up to 147. We further realized the permeations rate is quite high. It's about 3 orders of magnitude higher than the current membranes. So we do some molecular dynamic simulation. The result shows when the ions enter the pores, actually this hydrogen ions will be strongly interaction with the pore surface through the oxygen, the red one, and also the blue one, and the nitrogen atoms on the pore surface. Especially for the potassium, because they have the lower hydration allergy. So this shows the stronger bonding allergy with the pore surface. Moreover, after trapping this hydrogen ions, we can see the pore size of the pore molecule will be dramatically decreased down to 0.8 nanometers. We also found the pore size and the binding site are quite important for get the higher selectivity for the monovalent ions. For example, if we increase the pore size or if we remove the oxygen atom from the pore surface, actually you will see the permeance and also the selectivity for the ions will be dramatically decreased. So we want to know why 0.8 nanometer hydrogen pore are so important to achieve the high selectivity for the monovalent ions. So we do some theoretical calculation. We found a very new phenomenon. We call the shearing or squeezing of the hydrogen water layer. In other words, when two potassium ions approach each other, actually they can share the water layer. Otherwise, for sodium pairs or lithium pairs, actually they squeeze the water layers. We further do some quantitative calculation. As we choose the bottom figures, we can see within the range of from 4 to 6 angstrom, actually you found the totally different behaviors. For example, when the two potassium ions approach each other, you found that there is an attraction force. So this is totally different with the conventional or the classic textbook, because the textbook will tell you the ions with the same charge, they will repulse each other in the solution. Otherwise, here we show when there's two potassium ions approach each other within the range of 4 to 6 angstrom, actually you observe the attraction force. Why? Because they can share the water layers. However, in same way, you will find for the lithium and the sodium ions, actually they will repulse each other because they will squeeze the water layers. So we notice this distance 4 to 6 angstrom match well with the hydrogen pore size 8 angstrom. That's why we can obtain the high selectivity of the monovalent ions in this 8 angstrom hydrogen pores. So in coverage by above result, rather than use the hydrogen pores, we construct so-called solid state pore, also with the similar diameter of 8 angstrom. So we found this size is very much of the dimension of the hydrogen ions. We found a strong Coulomb blockage effect caused by single ion transport. So firstly, we check the conductance of the memory. We found in this 8 angstrom solid state pores, the conductance is much lower than the blank silicon nitride pores, but still 1 magnitude higher than that fully blocked silicon nitride pores. More importantly, as shown in the right figures, we can see in the solution of the soil concentration not greater than 0.1 mol per liter, we obtained the 100% selectivity of the cations, the positive ions. When we increase the soil concentration above 0.1 mol, actually the cation selectivity will dramatically decrease. This might attributed to the decrease or reduce the balance whenever we calculate the balance in 0.1 concentration, we found the estimate value is 8 angstrom. Remember, this 8 angstrom is very close to the size of our pores, solid state pores. So we further change the voltage. We can see at the low voltage, all these pores are closed. So as the left figure shows, so the conductance is very low. When we increase the voltage, actually the pore will be open. So we must get the largely increase the conductance. This is a typical nonlinear effect. More importantly, we also can see at the higher conductance state, we obtained a conductance ratio at the high conductance state. This is a typical feature of Coulomb blocking effect caused by single ion transport. We also see with increased the salt concentration in the solution, actually this nonlinear effect will be gradually disappear. So we use the molecular dynamic to simulate the single ion transport process. Finally, we found as the voltage increase, the resistance time of the ions within the pores will be decreased. As we show in the middle figure, the resistance time at the low voltage is about 180 picoseconds, and it will dramatically decrease to 30 picoseconds at the high voltage. And also the blocking property also decrease. More importantly, we found a so-called synergistic effect in this multiple system. So as we show here, when these doors are totally closed at the low voltage, you will see the transmembrane added area is quite high. It's about 5.5 kilocal per mole. However, as number of the open pores increase, actually as shows the middle and the right figures, the transmembrane added barrier for ion transport gradually decrease. This demonstrates the synergistic effect during this opening the pores. Actually, this phenomenon is very similar to the classic electroporation theory in the cell membrane. So in this electroporation theory, they said there is cooperative opening of the pores happens in the biological channels. So that means our modern system maybe will help us to understand what exactly happened for the ion transport mechanism in biological channels. And in the final section of my first part, we achieved the work memory scale work acceleration phenomena. So different with the previous work, actually we intentionally to change the benzene, the orientation of the benzene rings. This is the post-graduates. And we found we let this orientation of the benzene rings to perpendicular to the main plane. That means the flow across the main will be parallel to the benzene rings. So we use this unique strategies. We also control them as vertical pores, and we found the water acceleration phenomena. We can see from the middle and the right figures, the water transport in the vertical pores exceeds 3 times the value predicted by Hagen-Poiseuille models. So, except for water, we also use the isotropic diffusion experiment to confirm the water acceleration behaviors. As a result, we found the water diffusion rate in the vertical pores of post-molecular is higher than that in the planar pores, also equal higher than the nitrate pores. Moreover, we do some quantitative calculation. We found that the transmembrane of the algae barrier for the water is quite low. It's only 6.9 kilojoule per mole. It's much lower than the algae barrier of the water-free diffusion. So we want to know why can we realize the water acceleration by the membrane. So the first question we should answer if there is any hydrogen bonding taking effect. So we just add some so-called hydrogen bonding enhancer or hydrogen bonding disruptors. As a result, we show when we increase the hydrogen bonding between the water and the pore surface, actually the flux of the water will decrease. In other words, this result uncovers the polar pore walls significantly, not enhanced, rather than they just disrupt the hydrogen bonding, while the hydrophobic property reduce the friction. So we also do some quantitative comparisons with literature reported result. So we check the relationship between the enhancement ratio and the geometric parameter, that means the length versus against the diameter. We can say actually the water acceleration ability of our vertical pore is comparable to that carbon tube, as shown in this yellow circles in this phase. So we think the good water acceleration ability of our membrane comes from two factors. First is the low friction of the hydrophobic pores plus the hydrogen bonding disruption by the polar nitrate site. So the second part, I will talk about the organic molecular separation by membrane. So in this part, we want to use the self-anomaly strategy in organic molecular separation. Apart from the big successful for membrane-based separation in aqueous solution. So there are a lot of attention has been tracked recently in the field of organic molecular separation. This is because of the global demand for the handling of the organic solvent actually is comparable to the amount handled in the aqueous solution. However, if you check the literatures, most of work has been done in the aqueous solution. The big challenge is all the membrane used in the aqueous solution actually become unstable in the organic solvent. So the first question or first challenge we should solve is we should improve the stability in organic solvent. So we propose use the so-called all-conjugate framework to construct the porous membrane. Our result showed, except we improve the chemical and structural stability, we also found this rigid scaffold actually generate, as shown in the bottom picture, green color particles, actually we generate many interaction micropores. So these micropores definitely will help improve the permeance of organic solvent. So we also can see from this picture that actually there are higher porosity, also many pore interactions. So this one is totally different with the conventional used polyamide membranes. Because of this higher enriched interconnected pores, actually we obtained the higher solvent permeability, which much exceeded the current dense polymer membranes. Moreover, we do some molecular simulation. We can find a lot of continuous flow pathways in the permanent nanopores. All this follow so-called pore flow model rather than the dissolution diffusion model in conventional dense polymer-based membranes. Unfortunately, when we use this CMP membrane for organic solvent separations, we found that the precision is not too high. So the molecular weight cutoff is only 560 Dalton. So in order to further increase the selective ability, so we try to tune the pore size of CMP membranes by use different methods. For example, we tried the chemical modification method. Unfortunately, we still difficult to shrink the size, pore size down to less than 9 nanometers. So now we think the precision of nanofiltration is not enough to separate the small organic molecules. So how we can do? So I think we need at least 2 requirements to realize precision separation of small organic molecules. First one, we should decrease the pore size down to the angstrom rather than nanometer. The second one, we need to take advantage of synergistic weight interactions inside of the pores. So our target is about the small molecular organic molecules. They are broadly used in petrochemistry and chemical engineering, like alkenes, aromatics, olefins, alcohols, also esters. So the first example in this part, we try to use well-known sulfide anomaly method. We found actually the membrane pore size is reduced from 1.8 nanometer to 6.7 angstrom through the stacking of the porous polylayer. So you can see this side, 6.7 angstrom, is following the range of small organic molecules. Normally they are in the range of from 4 angstrom to 7 angstrom. So this one becomes promising for the separation of small organic molecules. So then we tested the common used solvent, 11 common used solvent, including the polar and the non-polar molecules. We found for the all polar molecules, like the alcohol, they could permeate the membrane as comparison for the non-polar molecules like alkene, aromatics, and also ester. They cannot permeate the membrane. We further tried the binary mixture of the ethanol, heptane, ethanol, toluene, and ethanol acid tetrabutene ester system. We all successfully achieved efficient separation of the polar and non-polar solvent. For instance, all these three systems, we found more than 19% ethanol selectivity in the products. So why the polar solvent can be preferred penetrate through this film? So we do some simulation calculation or theoretical calculation. as shown here, when the polar solvent enters the pores, actually the allergy barrier will dramatically decrease by Coulomb interaction between the polar solvent and the polar lightning groups on the pore surface. As a result, we think this is the main reason for porosity discrimination. We also tested the universality of our membrane in separation of 33 solvent pairs. We found if the porosity difference larger, actually we get the better selectivity. Moreover, we all see this solvent pairs, actually the separation factor is 1 or 2 order of magnitude higher than current use reversible osmosis membranes. We further fabricated the large area tubular membranes. We found the selectivity a little bit drops due to the defect of the large scale manufacture. However, the selectivity of the ethanol from the mixture of ethanol alkene scale higher than 10. So this result shows maybe this membrane has the potential for the real industry applications. We further want to tune or modulate the stacking distance and the pore surface property of the Prof membrane through the polymerization of the plenary and non-plenary monomers. We found after introduction of the non-plenary monomers in the two-dimensional membranes, actually we successfully tune the interlayer spacings. So we also try to separate then we can successfully obtain the selectively permission of the aromatics over the alkenes. We also try to separate the xylene isomer with identical size and physicochemistry property. So then we try to tune the stacking distance of two-dimensional graphene membrane, because as we know, the dimension of xylene isomer is about 5 to 7 angstrom. Actually, we found the simple thermal reduction is very efficient way, so we can tune the interlayer distance from the 8 angstrom to 6 angstrom. So then we realize the separation of xylene isomer with a separation factor up to 3. We also notice that permeance of this membrane is 1 or 2 orders magnitude higher than the current reverse osmosis membranes. So in the final example, we introduced a new cross-link method between inside this so-called covalent triazine framework membranes. So this is also one type of the Prof receptor. There is some ligation groups in the middle. However, the target of this work is why we want to decrease the out of hand swelling in the oil solvent. So first of all, we characterize the cross-link effect by the electroparamagnetic resonance and also solid-state nuclear magnetic resonance spectroscopy. So through this EPR result, we can see a strongly enhanced this peak. This one is attributed to stronger electron coupling, decolonizations after cross-link. So we also found a new peak at 110 ppm appears in the MR spectroscopy. This one comes from the strong coupling between the adjacent benzene rings after cross-link. So we also checked the mechanic strength of the cross-linked film. We found with the cross-link temperature increase, actually the mechanical strength of the memory also increased. To be specifically, the memory cross-link at 400 degrees C, you see the mechanical strength is very similar to common Prof memories. If we further increase the cross-link temperature to 450s, we found that the mechanical strength will be decreased, otherwise decreased. This is also easily understood because the high temperature will cause the damage on the conjugate framework. Are very important phenomena that is found. Whatever the cross-link temperature, actually you found the pore size of this cross-linked memory remains unchanged in the dry state, as shown in the left pictures. However, if you immerse this cross-linked memory in organic solvent, you will find a lysotropic swelling behaviors as the right figure shows. That means in-plane swelling, they are almost small, but out of plane swelling is quite big for this memory. This is also easy to understood because the organic solvents can penetrate interlayers, so they increase the swelling property. Whatever we can say, with the increased cross-link temperature, you found that the out-of-plane swelling will gradually decrease. In another word, actually we can control the swelling degree, also control the interlayer spacing in the organic solution by using the different cross-link temperature. Then we also can control the pore size. So then we tried the permeance and the selectivity of this cross-linked memory in the organic solvent. We found that the permeance decreased, but the selectivity also increased. To be specifically the memory and cross-linked at 400 degrees, we can see this memory exhibit more than 90% for a typical molecular we call as PIPB rejection rate. We also found that this cross-link memory are very stable in long-term organic solvent separation environment. We also try to use this cross-linked CPF memory for separating the small organic molecules. So we select 60 popularly used small organic molecules. We found that truly sharp the cutoff of the molecular weight with the molecular weight 200 Daltons. So this result shows our memory has the good ability to separate or precisely separate the small organic molecules. So we also check this phenomena or this property by using simulate crude oil as the right part said. We still can observe the clear molecular weight dependent on selectivity. And as comparison, so we also tried the memory without cross-link. We can see there is no any selectivity is to be obtained. So finally, we try to use our cross-linked memory for in the field of the complex crude oil separation. Without any dilution, so we tried the shell oil from Tianjin Dagang with an API value of 29. We found two very important result for our film. The first film, for all the cross-linked film, they have the ability to reach the light component with boiling point below 340 degrees C. The second important result is the highest carbon number will gradually decrease from 40 in the crude oil to 30 and finally to 20 in the permeate. In other words, if we control the cross-link degree or we control the cross-link temperature, we can realize the fluctuations of the crude oils into the different components. So, in summary, we developed the molecular separation memories to meet the demands for the fine separation, such as organic solvent nanofiltration, other separation, aromatic and fatty separation, xylene separation, and crude oil separation. So, what we will do in the future? First of all, we want to develop the new mechanism in nano-fluid theory. We suppose that the nano-fluid theory is the fundamental basis for the design the memory material and the processing with optimal performance. As we already know, compared with the classic theory, actually in the nano confinement, you need to add a lot of new atoms. They come from the strong carbon, they come from the rich interfacial interactions, also the short-range interactions. Second important interaction for the theory part is we want to develop some new transport mechanism in organic nanofluid. We think that this is quite important for our final target. We realized separate small organic molecules in organic solvent. However, if you check all the literatures, most work are related or associated with the nanofluid theory in aqueous solution. Recently, we published the first work in this area, which shows there is a large difference between the organic and inorganic, organic and aqueous solutions. So for the real application, we think now is the time transition from the aqueous to organics. So encouraged by seawater desalination by memory, we suppose the replacement of the desalination process with the memory will be lacks the breakthrough in memory technique applications. Finally, armed with the developed nanofluid system, we will challenge our ultimate goals. We will try to separate the molecules and the ions with extremely identical structures, size, as well physicochemical properties like isomer separation, chiral separation, also isotope separation. And based on our new knowledge about, for example, the dynamic pores, the polar and hydropore carbons, also biomimic channels. In the final part, I would like to thank my collaborator, Professor Lian Sanming, and my student for the hard workers. With the hard worker, I cannot tell this non-story here. Thank you for your attention.
This talk is, I think, is very impressive, informative, and very nice talk. Now the time is for the comments or questions. Please.
Thank you for your lively and in-depth presentation. Could you back to slide 26, please? I wonder. was very wonderful to see sharing and squeezing in-depth understanding of your team. I want to ask how material can affect this sharing and squeezing for example, for lithium, if they can change the sharing or the squeezing.
Yeah, very good question. I think that this one becomes the different instruction of the hydrogen layers of these ions. If you check the potassium, you will find that this hydrogen layers actually is flexible because from the theory, for the potassium ions they have a large size, so the hydrogen layer is more like flexible. But for the sodium and lithium, because their diameter is very small, and their hydrogen layer is very solid, or you can say it's rigid. So that means when you approach each other, actually, also because of the low hydration element. So in other words, for the hydrogen layer of the potassium, they are easy to deform and to share this hydrated water layer. But for lithium and sodium, they are cannot. So that's the reason. One should sharing the water layers, the other one should squeezing the water layer. Thank you.
Thank you. And may I ask another question about if the dynamic port can help us for controlling the ion?
Yeah, this is, you see, because, this dynamic pores actually is quite important. For example, what means dynamic pores? That means the hybrid ions can be absorbed inside of the pores. So without such as dynamic hybrid pores, actually the pore size is too big. So they will decrease the discrimination ability for these ions. As here we shows, when we increase the size of the pores, you will see the discrimination ability will decrease.
Thank you.
Thank you.
In your part on ion sieving, you explained that the pores become smaller due to a water layer interacting with the OH groups. My question is, can also anions or cations electrostatically attached to the surface bring such a pore narrowing? I expect that there is a theta potential at the surface.
Very good question. Actually, because of the time limitation, I didn't explain this phenomena very well and in lot of the details. You see here, so we actually tried different ions. For example, we firstly absorption of the potassium ions onto the walls. Then we found actually the sodium also become attractive. So as we said, if we introduce a large type of the ions, firstly reabsorb onto the pore walls, actually we also can tune the interaction or selectivity of a larger ion transport. Thank you.
Thank you.
Any question or comment?
Very wonderful talk. Thank you very much. I have one question about the last slides. You show there is difference for the solvent and water through the nanofluid. So I would like to know what's the main difference between the solvent and water. Last slide.
Yeah, one moment. Yeah, we see. This is the difference. We can see because because the viscosity is totally different between the water and here we choose the water and the organic solvent. You will see the deviations from the linear relationship to like this curve phenomena, because the viscosity is different between the aqueous solution and also the organic solvent. Thank you.
Yes, I see. Thank you.
Okay, I think this is more than 5 minutes, so because we will go to the close boundary. So that's